So we had another round of deadlines this morning. So as always, just a reminder, if you didn't complete like project 2, task 3, where we have the actual deadline, you need a recovery opportunity. Just for those of you, in case there's someone who is using their first recovery opportunity and isn't aware, I'd like to remind you every Wednesday. Those do have to be processed by me manually. It's either tonight or tomorrow morning I'll process those. So right now, Autolab isn't accepting your submissions anymore. But once I process all those and add all the extensions manually into Autolab, that'll open up again. You can start submitting again if you're in that situation. Hopefully nobody's in that situation. I haven't looked at the numbers for this one yet. But hopefully very few of you are in that situation. At this point in this semester, if you made it this far, you're usually making it the whole way. And most of you who are surviving this long aren't using recovery opportunities anymore, for the most part. So hopefully that applies to somewhere between 0 and close to 0 of you. All right, so let's talk about recursion. Any questions before we get into slides? Y'all are talkative today. We can just chat for a while, too. Yeah. When I got coconut malt, it was the deepest embarrassment of my life.
Are you gonna go through the songs again?
Oh yeah, I could. Oh, fuck. That's what I wanted to do. I'll do it on Friday at least. I forgot to put my solution code on here so I could run it on the current data. But I'll pull that up at least. The guy who coconut mauled me is now a TA, for what it's worth. Incidentally.
It's not like the if they fool you, they become a TA.
That's about how it works. Some TAs got to become TAs by breaking Autolab, so that works too.
Wow.
I don't know how much I want to talk about it, but by cheating the system and being able to get credit without actually doing the assignment. So to do that, usually this is what they'll do. They'll do the assignment legit, like straight up get credit, and then break Autolab and then tell me about it. And my reaction is usually like, you should be a TA. Like, let me give you money to do this for real. That's how I got some of the TAs. They just started breaking things. I'm like, yeah, I want you on my side, not against me. So we had the song ratings. We have quite a few ratings. I had a few bug fixes that I found out as we all submitted ratings on Monday. So the rating CSV is working a lot better now. If you submitted a song with commas, like commas are removed now because that breaks all the CSV parsing. Because we're not actually parsing CSV, we're just splitting on commas. So I just removed all the commas. And we do handle Unicode now. So we don't have all those ridiculous characters. We actually have proper Unicode now instead of rendering that as just a bunch of random bytes pretending to be ASCII. So if you take all this, copy it. I forgot to put my solution code on this laptop. I'll run it on Friday. It'll be good April Fool's thing. We'll just listen to music for a little bit. And copy this into your submission and run that main code in music.main. And you'll be able to see what the top songs are for this semester. Uncomment some of the stuff in that main method too. So we can find out what the top songs. Right now, the top song is, if I can remember, J. Cole, No Role Models. Straight fives. Everybody loves this song, apparently. I didn't realize how popular this song was, or if it's one person who figured out how to spam the thing. But this is our #1 song right now. So if you're interested in the songs, keep putting in ratings. You can keep rating stuff. I like having real data to work with. It makes the assignment more exciting, I think, than just having fake data or data from old semesters. Let's get with this semester, what you all like the most. So anyway, that's still up. And let's do some slides. Where am I? Here. For UB hacking this weekend, can you just walk into Davis and look around, right? I think unofficially, like there's not going to be security or anything. Like you can do that. But if you're going to show up, like just register. You can register. It doesn't cost anything to register. Just put down your name. Even if you're just going to poke around, there's no harm in also registering if you're going to do that. Like it doesn't cost you anything, and then they can, like, the higher numbers of registration also helps. Like this is the amount of interest in this that helps them go to sponsors too. So if you're actually going to the event, like just register so they can have a record of that. It helps out everybody. I don't even know what I'm looking at. If I miss the quiz for LO2, I will have to use a recovery opportunity, right? If you missed it the week before break, you can still take it next week in the second chance lab. That does not require a recovery opportunity. So you get 2 chances at each quiz and each interview, and you kind of get the 2 deadlines for the homeworks. You get that free 1-week extension on each task. Those are all free. Those don't take recovery opportunities. But if you need a 3rd chance on anything, then you need to use a recovery opportunity. So if you take lab next week, everybody gets lab next week for free. If you didn't get credit for the quiz or interview, both quiz and interview, you go to lab next week. That opportunity is free. If you fail it again, then it's a recovery opportunity. Oh, and Ren already answered you. I should just read the answers in here. Everything I said was already said in chat.
Yeah.
Oh, I have an event on Saturday. Go there. I forget what time. I think 4. I have an event on Saturday, UB hacking. Be there. It's going to be lit. You need to put a resume for the UB hacking form? I'm not aware.
Yeah.
You do have to? Okay.
Not this week.
If you fail the second interview twice, how to use a recovery opportunity, it'll be automatic. I'll send you an email saying that you used a recovery opportunity, and then a TA will follow up with another email with scheduling details. All right, let's do some slides. Let's get into some content. So we're talking about recursion this week. A recursive method is a method that calls itself, or a recursive function, or we even talked about algorithms on Monday, where we were talking about algorithms separate of any programming language, separate of any code, and just talking about the base algorithm itself without code. When it's code, it's either going to be functions or methods. I'm usually going to say methods, but all the same applies to functions as well. You can have recursive functions. So my strategy of writing these recursive methods, which is what you'll end up doing, what you have to do in homework, is 4 ingredients that you mix together, and out comes your recursive algorithm. First ingredient is write a base case. Think of some trivial input-output behavior for your method and write that input-output behavior. This should be very simple. For merge sort, it was, if you give me a list of length 1, I'm just going to return it because it's already sorted. If I'm summing up the values from 1 to n, which is the example today, and you give me an n of 0, and I'm summing up, well, it's technically 0 to n, and you're telling me to sum up all the values up to 0, I'm just going to return 0. Trivial input-output behavior. So what's the easiest thing? For your homework, process all of this list of strings, all these lines from a file. Well, if you give me the empty list, I'm already done. That's an easy day. That's your base case. Base case should be the easiest thing. You shouldn't be doing any processing, really, just the simplest possible input. Write that as your base case. Give me an empty list of lines from a file to process. Well, I'm already done. It's an empty, there's no data here. Done. I'm just going to return some empty value, some nothing. So very simple stuff. Usually zeros, ones, empty string, empty list, empty map. Those are usually your base cases where you have to do absolutely nothing. For our sorting, for merge sort, our base case could even be a list of, oh, that doesn't actually work. A list of size 0, that doesn't work. We need a list of size 1, so we hit the base case. Then you're going to add a conditional. So the top level logic of your algorithm of your recursive method is typically if we've reached the base case, return the base case output. If the list is empty, return empty list or 0 or whatever. Else, then you're going to, in that else block, get into your recursive step, which is going to include at least one recursive call of the algorithm, of the method itself. So the top level is if base case, trivial return value, else the rest of the logic of your method. In that logic, we're going to get to our next two ingredients. We're going to assume that any recursive call you make will return the correct value. So if I have to if I have something that I want to process, I'm going to, and I don't feel like processing it, that's really the power of recursion. I don't feel like actually doing work. I'm just going to make a recursive call and just assume that the work got done at some point and that returned the right value. And then I'm going to make sure all of my logic flows from that. So if I have this magical box of my method, my recursive method, that I can just call it and it always returns the right answer, I'm going to call that, assume it returns the right answer, and then build my method based on that assumption. I'm just going to assume it returns the right answer and then build everything around that recursive call. If that recursive call does in fact return the right answer, then you should in fact return the right answer also. If both of those things are true, and the fourth ingredient, and we hit the fourth ingredient, then your algorithm is going to be correct. So the fourth ingredient, is making sure your recursive calls always get closer to the base case. If your recursive calls always get closer to the base case, and I recommend getting some, I'll wait till my next slide to say that. Always get closer to your base case, and then you'll eventually reach the base case, and you'll have a successful recursive algorithm. So if this weren't one of the ingredients, what I would do writing my recursive method is I get an input, some input x. I'm going to make my recursive call and say recursive call of x, and whatever you return, I'm just going to return it. That's not allowed. So we have to get closer to the base case. We can't just take our input and make a recursive call the method itself with the same input, because we're never going to get closer to the base case, and it's just going to keep going on until infinity. Like, we're never going to reach that base case. So we have to eventually reach the base case of our recursive calls, because the base case is the only time where we're not making another recursive call. We have to eventually get things to stop when we hit the base case and then start returning, and then our logic kicks in and everything magically works. No, I guess I'm not waiting until my next slide. I know it's one of these slides. I'll just say it right here. And when you're getting closer to your base case, get at least, oh, I know where it is. Never mind. Let's just get into it. So let's write a recursive method. This is like one of the simplest recursive methods I could think of. It's just to introduce the idea of recursion, and then we'll get into some more complex ones that are going to be more like your homework examples. But just to get a first example of recursion, I want to write a method sum to n, which is going to sum up all the values technically from 0 to n, even though I word it from 1 to n, but 0 is a valid input, so we'll say 0 to n. So if I call sum to n of 3, I want to sum up the values 1 plus 2 plus 3, and I would expect this to return 6. So this is the method we want to write, and we want to write it using recursion. So I'm going to go to my 4 ingredients for successful recursion, and I'm going to add those to this method. First, I'm going to start with a base case, which is a trivial input-output behavior. So what's the easiest possible thing to take the sum from technically 0 to n of? Well, if you give me 0, I'm just going to return 0. The sum of 0 up until n, where n is 0, is just 0. There's no work to be done. I don't have to do any math or anything. We could also have a base case of 1 if I want to say if n equals 1, return 1, else if n is less than or equal to 0, return 0. And I'm getting rid of negative numbers here. If somebody wants to be smart and give me -5 as an input, I'm going to wipe that away by saying, okay, the sum of values from 0 to -5, I'm just going to return 0. Like, you're not allowed to use negative numbers. So I have the less than or equal just to handle those cases, so I don't get in trouble if somebody gives me a negative number. Now that we have our base case, let's add the next two ingredients. We're going to assume that our recursive calls are correct. So if we're not in the base case, we're going to get in our recursive step, the rest of our logic. And I'm going to assume any recursive calls I make are going to return the right answer. So I have this power. When I'm writing the recursive step, I have the power to make recursive calls. And I can assume that they're going to return the right answer as long as they get closer to the base case. It's going to be successful recursion. So I'm going to make a recursive call. That's the power that I have. That's my recursive assumption that I can make. That I can make recursive calls. They have to get closer to the base case. And I always recommend the easiest way to write recursive methods is think of the smallest amount of work that you have to do to get your recursive call one step closer to the base case. So do as little as possible to be able to get the input knocked down a little bit closer to the base case. For this, since we're working with integers, our base case is 0, and we're assuming n is positive because less than negative numbers I'm going to throw in my base case. So I have some positive integer. If I want to get this as small a step closer to the base case as possible, I'm going to subtract it by 1. That's going to get me just a little bit closer to the base case. So my recursive call, just a little bit closer to the base case, n minus 1. Make a recursive call, n minus 1. And then I'm going to build all my logic around that recursive call. For your homework, the smallest amount of work you can possibly do and get closer to your base case of an empty list is get one element out of that list. Process one line of the file. That's your entire goal. You process one line of that file, and then make a recursive call with all of the lines except that one line that you processed. You assume that that recursive call works, and then build your logic around that. And that's all you have to really do is write your method, write the code to be able to process one single line, and then recursion kicks in after that and processes the entire file, the entire list for you. For this, I'm going to process one value of this integer. I'm going to make subtract n by 1, and process just that one value of n. So if I have to sum up, I can think of this the other way around. I have to sum up the values from n, n minus 1, n minus 2, n minus 3, all the way down to 0 or 1. Well, the way we're coding is 0, so I'll say 0. n minus 1, n plus n minus 1 plus n minus 2 plus n minus 3, all the way down to 0. That's my goal. So if I make this recursive call sum to n of n minus 1, I'm going to assume that that returns the correct value. The correct value is n minus 1 plus n minus 2 plus n minus 3 plus n minus 4 plus n minus 5, all the way down to 0. If that returns the sum of all those values, and my current task is to return the sum of all those values plus n minus 1, n minus 2, all the way down, then I'm just going to add n to this. I assume this returns the sum of 0 to n minus 1. If I add n to it, I'm going to have the sum from 0 to n. So I assume my recursive call returns the correct answer, and then my logic kicks in to be able to take that partial solution that's one step closer to the base case, and then process it a little bit more to be able to get the full solution that I'm looking for. And I got ahead of my slide a little bit on that one. So we're just assuming that it works, and then building my logic around that. If sum to n works, then here's what I have to do to finish it. If merge sort works, and I'm cutting the list size in half, which gets me closer to my base case, then I assume that works, assume those are sorted lists, and then call merge, which is going to assume those lists are sorted, and then merge them into one bigger sorted list. And you have to have a little faith until you can see how this actually works. And again, by the end of the week, I'm hoping I'll get you to be able to see it. Today, we're going to look at this in a memory diagram, which I think shows it a lot more clearly what the hell is even happening here. But at first, have some faith in recursion. Take those 4 ingredients, try to get a little closer to your base case, and then process the minimal amount of work that you have to do in your recursive step, and then get closer to that base case. Base case is trivial input-output, and then by magic, it just works. So let's dispel some of that magic. So for the base case, the recursive call is true. If I call sum to n, where n is 1, I'm saying 1 plus sum to n of 0, and I'm assuming sum to n of 0 is returning the correct answer. Well, that's the base case. Of course it's true. Of course, sum to n of 0 is going to return the right answer. So our assumption is true in that case. It's very true. It's obviously true. It's trivially true. Because it's the sum of 0 plus 0 up to 0 is 0. We're just adding a bunch of zeros. So that's going to be true. And then I'm going to add 1 to it and return 1. So now the call of sum to n of 2, where n is 2, I'm going to take 2 plus sum to n of 1. Well, we just walked through sum to n of 1 and saw that that is going to return 1. So our assumption happened to be true. We're going to add 2 to it and return 3. Well, now when we had an input of 3 and called sum to n of 2, well, we just saw that sum of n of 2 does, in fact, return the right answer. We're going to add 3 to that and return 6. We're going to, in fact, return the right answer each time. That assumption will be true as long as we have those 4 steps to our recursion. We're getting closer to our base case. The base case is correct. We're assuming that our recursive call returns the right answer, and our logic is built around that assumption and computes the correct answer after that. So let's see this all in a memory diagram and visualize it. Who's ready for a memory diagram? It's been a while since before break. Or the value of n be increased? Well, yeah, that'll make more sense when, or Nicholas will answer it actually. That'll make more sense with the memory diagram. So n is decreasing, but when the math is being done, it will actually be increasing, and we'll see why. So the TLDR of that one is we're going to add a whole bunch of frames to the stack and just go down the recursive calls, and then when the base case returns and we return back up the recursive calls, that's where we're actually doing the math. So we're actually going to sum in the order of 0 plus 1 plus 2 plus 3, even though we're making calls in the order 3 plus 2 plus 1 plus 0. So this starts out fine enough. Well, we've done this plenty of times. We have this line, which is going to put a variable on the stack, call a method, which is going to put a frame on the stack, pass the argument into the parameter. So we have n equals 3 inside this stack frame. And we have our arrow to show that it will return into the variable result. So nothing new there. We've been doing that since LO1. Nothing new here. Where things get new is when we hit the recursive call. So, and just a side note, I'm not going to draw the dash boxes for the code blocks, for the conditional. Whenever we don't declare any variables inside a code block, you don't have to draw the dashed lines, because we would have a dashed box that's empty. If it's an empty box, let's not draw them. Let's agree to just not draw them. This only happens with conditionals. With loops, you at the very least have the looping variable That's part of the loop. The for variable in data structure, that variable is going to be in that loop block. So for loops, you always have it. For conditionals, if there's no variables declared inside the block, let's not draw the empty dashed box. And that's fair game on your quizzes as well. By the way, for your LO3 quiz, I can't believe we're on LO3 already. Semester's flying. For your LO3 quiz, you can expect a recursive example like this and an immutability example like we'll do next week, where we'll put objects on the heap that are immutable. Obviously, we haven't talked about immutability yet, so that's coming up. But recursion and immutability, functions will not be on the quiz. I didn't show you any memory diagrams with functions, with first-order functions, passing functions. I didn't show you any of that, and that's because we're just not doing it. Paul and I talked about it for a while, and we decided it's dumb, so we're not going to do it. We argued for a bit about how to represent a function in the heap, because it is an object in heap space, and we couldn't find a good answer that we liked, so we just said, you know what, let's not. Let's not put everybody through that. We're going to put you through enough with recursion mostly is going to be the bulk of the difficulty of the quiz. Because recursion is the most important thing that we want you to understand. We don't care if you don't understand how a function is represented on the heap, because Paul and I couldn't even agree how that works, so let's just not. But you'll be doing something like this on the quiz for sure, for LO3 quiz. Okay, so we get to our first recursive call, and this is where things start getting interesting. This is where we start seeing how recursion actually works, and we stop saying, oh, it'll just be true, just assume it's true, that'll be true, and it's magic. We're going to stop saying that at this point, because we're going to see how these recursive calls work. So we're calling sum to n of n minus 1. In this stack frame, n was 3, so n minus 1 is 2. We're going to call sum to n, add another stack frame to the stack because we have another method call. This works just the same as if we called a method with a completely different name. If we just have one method that calls another method, and we would put another frame on the stack, or we have constructors that call other constructors through inheritance, and we put new frames on the stack because a method called another method. Same thing here, but the method is calling itself. That's the only difference. It gives us a lot more power when it's calling itself, but physically, it's the same thing. The same thing's happening in memory. Everything's the same. For the notation, when we have a recursive method that's returning to itself, to another recursive thing, our arrows, we're not going to put it into a variable. This doesn't return any values into a variable. It might on the quiz. I think Paul's example, he did declare an intermediate variable to be able to return into that variable. But if the recursive methods are just returning into themselves, so whatever each thing returns, it's going into the other one, we're going to draw our arrow just going into the other stack frame. So that's our notation that we'll use, unless, even with the intermediate variable, you do the same thing. That's right. So even if we said val x equals n plus sum to n minus 1, we put that inside the stack frame, and the arrow, the return, is still going to go into the other frame. So that's the bit of notation for your quiz to remember. Otherwise, honestly, it's all the same as stuff we've been doing since LO1, just frames on the stack through method calls. The methods that are being called just happen to be calling themselves. That's the big difference with recursion. So the method called itself, we have n equals 2 in this stack frame. 2 is less than or equal to 0. Hopefully we can agree on, or is not less than or equal to 0. We can't agree on that because I can't even say it right. So we're going to get another recursive call, and we're going to have another stack frame that's sitting here on this same line waiting to be returned. So I'm going to keep these arrows just like I always do. I don't talk about the arrows, but I'm going to keep these the same way that I always do, where the arrows are where that stack frame is waiting for a return value. And gray means it's not the currently active stack frame, which means it's not the stack frame that's on the top of the stack. So only the frame on the top of the stack, bottom visually, is going to be the active stack frame. That's the only stack frame that can do anything. And all the grayed out ones are just sitting there waiting for this method call. So this stack frame, which is the sum to n with n equals 3, is waiting for sum to n of n equals 2 to return. And our first stack frame is waiting right here on this call. So we're going to have more arrows like that. This stack frame is going to call sum to n with the value 1, 2 minus 1. And we're just going to keep repeating this process. We keep adding frames to the stack until we reach that base case. So we have 3 stack frames just sitting here waiting for a return value. Each one of these stack frames has a different value of n, and they all made recursive calls for n minus 1 and just kept decrementing n until we get to the base case. So we have 4, technically 5 with our main stack frame, frames sitting on the stack just waiting for something to return anything, waiting on these method calls to return, these stack frames to return values so they can finish up their process. They're all sitting here waiting for this function to resolve, or this method to resolve. And once we hit the base case, we can finally do something. We can finally get something to happen. So with the base case just straight up returns 0. Trivial input-output behavior, that's how we want our base cases. Just, you gave me 0, I'm going to return 0. Don't even have to think about it. The base case just does its thing. So now that we actually have a frame returning, we can start going back up the recursion. The terminology, I don't know if this is official or anything, but the terminology I use is we go down the recursion when we're making recursive calls. Now that we hit the base case, we can go back up the recursion and start processing the recursive results. So this stack frame is going to return 0. This stack frame ends. It'll be crossed out on your quiz, but I'm going to keep this notation graying them out. So now this stack frame is active again where n is 1. And we're computing this line, n plus sum to n of 0. Sum to n of 0 just returned 0. N is 1 in this stack frame, so we have 1 plus 0, which is going to equal 1, and that's what we return. And we note that our assumption that a recursive call is going to return the right value was true. Sum to n of 0 did in fact return 0, and that's what we wanted it to return with that input. That input should return that output. We're going to return 1. So sum to n of 1 with n equals 1 is actually going to return 1. So guess what? We return up into the stack frame where n equals 2. That assumption that our recursive call was correct was actually correct. Recursion is actually working the way we expect it to work. So now our sum to n of 1 returned 1. Assumption's still correct. Something's working right. Something's working for us. Recursion's doing its job, and we're getting this working. This frame, n is 2. Sum to n of 1 returned 1. We're going to compute 2 plus 1. Hopefully we can agree is 3. So n of 2, sum to n of 2 returns 3 up to this stack frame. And this is why Paul did the intermediate variable. I kind of wish I did too, so we can remember what the return values were. That's going to return 3. We're back to this stack frame which was waiting for sum to n of 2 to return, got its return value, and it's ready to finish its processing. So it's going to say, OK, n plus sum to n of 2. Sum to n of 2 returned 3, which, hey, our assumption's still correct. We assumed it. We felt like it was magic, but look, it's actually working. It works the way we want it to work. And n is 3. So 3 plus 3, we're returning 6. And even at sum to n of 3, that did return 6. And our assumption, even our assumption of that was correct. Our recursive calls, we can go out to infinity. Well, we can go up to 2 to the 31st minus 1. And that assumption is always going to be true. Well, we technically can't do that. But that assumption is always going to be true because of the way the logic is going to return. We're always going to make a recursive call of n minus 1 and just wait for an answer. Eventually, we get down to n equals 0. That returns, and then our logic kicks in. That returns to n equals 1, that stack frame. It does its thing, just adds n to the solution, returns, and sum to n of 2 gets its return value of sum of n to 1, sum to n of 1, gets its return value, which is correct, does its processing, returns its correct value, sum to n of 3 gets its return value, does its processing, returns, and every step up this chain, we could go up to very large numbers. It's always going to be true. The recursive calls always are returning the right value because our logic is correct. So if this returns the right value, our logic kicks in and the bigger call returns its correct value. So if sum to n minus 1 is actually correct, sum to n of n does return the correct value because it's just adding the n. It's doing its little bit of processing and then returning. So if we do get sum to n of n minus 1 is correct, then sum to n of n is correct based on our logic. And sum to n of n minus 1 eventually gets to the base case, which is, of course, correct. So because sum to n of 0 is correct, our logic kicks in and makes sum of 0 plus 1, sum to n of 1 correct, sum to n of 2 correct, sum to n of 3, and it just keeps going out to infinity. And it's always going to be correct because we have those 4 ingredients. And then we print 6 to the screen. The hardest part about that is just remembering. When you're sitting for a quiz, we see this a bit on quizzes. You go through all that recursion, and you're thinking about recursion and putting frames on the stack, and where do my arrows go and everything. And you get to the end, and you forget to write 6. Just don't forget to write that. I think in a lot of cases, we let that slide, but it's an easy thing to forget. Yeah?
We're doing this by storing the answer in a variable, like you said Paul was going to do it. You would just take that line in the else block and like declare a variable there, say like result is equal to n plus sum to n.
Yeah. Yeah, so if I did result equals n plus sum to n of n minus 1, and then on the next line just put result and return it, then in each one of these stack frames, I would put my dashed box, put result, and then the result that I computed inside the dashed box inside the stack frame. That's how we would do that. Any questions about this? I'll give you a little time to digest this one. And don't, what do I want to say? It's one of those things. I fell into this trap a lot, so I feel compelled to give the warning of don't get caught up in this example being kind of simple. Like it's easy to ignore. I did do this in classes fairly, way too often, and it hurt me. I look at this and I say, I don't need recursion for that. You're just summing from 0 to n. Like I can do that with a loop, and then I don't pay attention to that example. But forget that we're just summing up values, summing up things that you could do easily in a loop. No, we wouldn't need recursion for this. We wouldn't use recursion for this if you're actually doing this. We would do this in a way simpler way. But focus on the recursion. How did that recursion work? How did those 4 steps of the recursion come together? And try to see how recursion itself works while you're looking at this example. And are there any questions on how that recursion works? Again, it's a very slippery topic. It takes a while to dispel that magic. But hopefully if I just repeat the 4 steps like 18 more times, you'll just be like, oh, I get it. Oh, what's up?
What do you mean by sum to the n of n?
Sum to n of n? What do you mean?
I think that you mentioned like sum to n of n, and then
sum to. Oh yeah. So I'm saying like sum to n of n. I'm saying like 3 would be my n.
Oh, okay.
And my goal for the top level call is to compute the sum to n of n where n equals 3. And I'm going to assume that sum to n of n minus 1, which would be 2, I'm going to assume that that's correct. And then if I can take that assumption and do a little bit of work and return the actual sum to n of 3, which was my n when I was saying that, where n is just the generic, like any number. If you give me any number, and I make my recursive call and get the sum to n of 1 minus, that number minus 1, then I'm going to add n to it, do my little bit of processing, and then be able to return the correct answer for any value n. So in this case, 3. You give me the task of summing up all the values from all the integers from 0 to 3, and I say, well, I have this magic recursion algorithm method that I'm going to call and say, give me the sum of all the values from 0 to 2. I'm going to assume that returns the right value. Then I'm going to slap 3 on top of it and then return that. And what I'm returning is the sum of 0 through 3. But my recursive call, I got the sum of the values from 0 to 2. So I just got to add 3 to that and then return it. So in general, I can go from any n minus 1, the correct solution of n minus 1, to the correct solution of n, or n plus 1 if you want to. Let's not do that. So I can use that logic any number of times. I start with 0. We need some place for things to start. We start with 0 and say the sum of 0 to 0 is 0. Return that. And then with that knowledge, I can add 1 to it to get the sum from 0 to 1. I can add 2 to that to get the sum of 0 to 2. I can add 3 to that to get the sum of 0 to 3. I can add 4 to that, and so on, all the way up to any arbitrary number we can think of, any positive integer that we can think of, in theory. In code, this would break a few ways before we get to infinity. But in theoretically, we could go out to infinity with this. Just keep adding the next integer and returning. So the only amount of work we actually have to do in our code is just add n. And then let recursion handle everything else through multiple recursive calls. If n is 3, we're going to make 3 recursive calls after the first call. And then the recursion with all those stack frames is going to kick in. If we have n equals 100, I call sum to n of 100. We're going to have 100 stack frames, and each stack frame only adds 1 integer. But together, they add all 100 integers. Or 101, because we're adding 0 as well. Does that hopefully answer your question?
Thank you.
Okay. Anything else? Is this starting to make sense? Yes?
So is recursion like similar to like merge sort? So because like when we in like last lecture, we learned about how like I guess you break down the list. Is that kind of like what recursion is, similar to merge sorting?
Yeah. So merge sort uses recursion. Merge sort is a recursive method because it calls itself. So merge sort, the method, takes it has the base case of a list of size 1, and then the recursive step will split the list in half into 2 lists of half the size, and then call itself twice, once on each of those lists. So because merge sort calls itself, that makes it a recursive method. So that's why we introduced. So the segue is, I'm starting to rethink starting with merge sort. That's pretty complex for your first recursive algorithm. But the idea is segueing from sorting. We just talked about selection sort and first order functions and type parameters. And then we continue talking about sorting, but sprinkle in recursion. And then scale down to a simpler recursion. Strip out the sorting and then just talk about recursion today. That's the idea. I don't know how. I want to rethink that for next semester. But that's the idea of the flow of lectures. But that was a recursive algorithm. Can you show how to sum to n of 2 equals 3? So if we called sum to n of 2 right here, we would go right to this stack frame. Like that would be the first frame. We would still have the recursive calls down to 0, but we would start at that one, and the n equals 3 stack frame just wouldn't be there. And then we would get to the base case of 0, return 0, add 1 to it, return 1, add 2 to it, return 3, and then that's what would be returned for sum to n of 2. For recursive calls, our arrows are going to return to the previous stack frame. So that's the notation we're going to use for recursion. So when we see this, like, I know this is a recursive method. If I see your memory diagram and I see something like this, where I got a bunch of frames with the same name and they're all pointing to each other with their return values, that's cluing me in that this is a recursive method. I know you're calling a recursive method there. Everyone feeling all right about this one? Okay. When writing your recursion, I think it was the last step that I talked about today, right? Making sure your recursive calls always get closer to your base case. That's super duper important. How important? To always reach your base case, you must always reach your base case, because that's the only reason why we stopped making recursive calls. That's the only reason why we stopped adding frames to the stack, is that we hit our base case. So what if we modified our code a little bit, just didn't have a base case? And now with this modified code, we get to the part where we're at. All the recursive calls work the same up until n equals 0. But now when n equals 0, we don't hit a base case because a base case doesn't exist. So now what's going to happen is the method calls itself, then the method calls itself, then the method calls itself, and there's nothing to stop the process. It's going to continue to call itself for how long? It's going to just keep going and going and going, putting new frame on the stack, frame on the stack, frame on the stack, frame on the stack. Just going to keep going and going and going. If it doesn't hit your base case, and this is where we hit our stack overflow error. Eventually, we're going to run out of stack space. We're going to ask for more stack space. We need room for another stack frame. And the JVM is going to be like, you've had enough. Like, you've used up all the stack space I gave you. You're done. You're not getting any more stack space. And our program goes, oh, crap, what am I supposed to do? And it's going to throw a stack overflow error and just say, you used up too much stack space. You wrote infinite recursion is what this is. And just kept putting frames on the stack until you ran out of memory. Program crashes and nothing works after that. So if you see a stack overflow error or ran out of stack space or anything to that effect, look for your infinite recursion and make sure that you're hitting your base case, because you're not at that point. I have never, ever, ever seen a stack overflow error that wasn't caused by infinite recursion. It's always going to be infinite recursion. You'd have to be doing something really silly. Like, you get a lot of stack space. You can put thousands of frames on the stack before you overflow the stack. In normal programming, you're never going to do that. But if you hit infinite recursion, you're going to get there immediately. So if you see the stack overflow error when you're writing your recursive methods, the first thing you want to look for is, why am I not reaching my base case? Because you're not hitting your base case in that situation. And I kind of purposely ran out of time because I don't want to talk about this example. Maybe I'll talk about it on Friday. But this example, you can look through the slides and take a look at it. It's also in the repo. But here's a more complex recursive method. But it's a tad too complex. It's a bit overshooting. So I don't really want to talk about it. On Friday, we'll do something more difficult than just summing up integers. We'll use some data structures, but not quite this insane. I don't really want to use this example. But I kept it in the slides in case you want to take a look at it. But it uses quite a bit of stuff. So let's just go to this thing. And as usual, once you submit, you're good to go. Have a great day, and I'll see you Friday.